So, all right, so I want to share my screen. And you should see this PowerPoint. This is pretty much where we left off last time, I believe. Please correct me if I'm wrong. It was right in this area where you did, for homework, a practice problem on calculating the rate law based off of some experiment, and then calculating the rate constant K from that experimental data. So we talked a little bit. Any questions on that? All right. Okay, so now what we want to do is we want to think about what those rate laws are and how we might be able to get some more information from those rate laws. And specifically, can we get some information on how the concentration, for example, changes in time? Because for rate laws, the rate law really only says something about the rate of a chemical reaction and how it changes with the changing of an initial concentration of some reactant. So here I have some generalized rate law, which, by the way, as soon as you see the rate law in this form, it kind of gives you an indication of what the reaction might be. So this reaction could be something like A goes to B, or A goes to B plus C plus whatever, or it could be 2A goes to whatever, or it could be 5A. It doesn't matter, right? That stoichiometric coefficient is there, and it's important for when you're relating the rates of consumption and production of any of the products and reactants. That stoichiometric coefficient comes into play. But for the rate law, remember, this power dependency doesn't necessarily relate to that stoichiometric coefficient. So that power dependency here, X, has to be found experimentally. So that's experimentally determined. All right. And like I said, this rate law talks about how the rate of a reaction changes with changing concentration. But it doesn't say anything about how concentration changes in time. So we want to introduce the next bunch of important equations, which are called the integrated rate laws. Okay. So without further ado, we go to the next plate. And here I have the integrated rate laws in this table. And by the way, I might mention or remind you guys that for the in-class exams 1, 2, and 3, you'll be able to use a 3x5 card with any equations on it that you might need for the exam. And it might be a good idea to recreate this table here on your 3x5 card. So this first column, I have the order, and you should have a pretty good idea what that means or refers to. That's that power dependency in the rate law. That's what the order is. And in Chem 201, we consider pretty much these three possibilities: zeroth, first, and second order. Does that mean they're the only ones? No. We can have any fraction. It could even be negative. It could be any value. but these guys serve to be representative, these three, and these are the ones that are usually discussed in Chem 201, second semester general chemistry. All right, so we know what the rate law looks like. For example, if I have some reaction, A goes to B, then as soon as I write down that reaction, I've defined my reactants and my products. So I know the form of the rate law right away. So it's going to be rate equals some rate constant, K, times the initial concentration of all the reactants to some power. Well, there's only one reactant here, A, so this is the possible rate law. And down here, I have the three most common ones that you find in Chem 201. So the next column is the rate law itself. So the rate here in units of molarities per second, that's the units that we're going to try to use for rate of any reaction. And then we have that equals our three possibilities, 0, first, and second order dependency. Also, you see how the units of K change depending on the overall order of the rate law. And we talked about that before. And as usual, if you have any questions, please just go ahead and holler. Okay, so the next column here is where we have the integrated rate laws. Now, these integrated rate laws come about through integration of the rate law. And you see in these forms, we lose all reference to rates. There's no R's in any one of these equations. And I should also mention that these integrated rate laws or equations are infinite point functions, which means that they're functions and they have an infinite number of points. For example, this first integrated rate law, and you can think about these as linear functions. So y equals mx plus b, you'll recall from math. And this is the equation of a line, and you can have an infinite number of points in that line. And when I say points, I'm referring to XY points. So Y I can represent with a running index of I, and that's connected to X with a running index of I. So that I can run from 1 to infinity because there's an infinite number of points in this function. And X, as you recall from math, is the independent variable. Y is the dependent variable. So you give me an X, right? And I put that X value in here. And then I'll tell you the Y that's associated with it because I can calculate it given the slope and the intercept. And so this is all kind of or should be kind of a review for you guys in your math and math equations and functions and what that means. So again, this is an infinite point function. I got a dependent, independent variable. Once you name one of those variables, that locks that equation into 1 point, and you can solve for the associated Y once you know the X. All right, any questions on that so far? All right, so let's take a look at the subscripts in these integrated rate laws and show what they mean. Now, for the 0th order integrated rate law, this mathematical function tells you how the concentration at some time t, and that t is a time in the future. So the concentration at time t is represented like we have here with A in brackets. That's to represent concentration in chemistry. And then the subscript T means that's the concentration at that time. Now that's found to equal minus K. K here in the integrated rate law is the same as the K here in the rate law. T is my independent variable, time, and that can run again from some initial time to some final time and any time in between. And then the last term is associated with the initial concentration, or the concentration at t equals 0 seconds, or the initial concentration. So again, once you know how a reaction behaves, whether it's 0th, 1st, or 2nd order, then you know how the concentration of that reactant is going to evolve in time. And so forth. So for the 1st order integrated rate law, I see that it's the log of the concentration that's directly related to time. And for the 2nd order integrated rate law, I see the relationship is 1 over the concentration related to how time changes. And again, there's an initial concentration value for both of those integrated rate laws. Any questions on the integrated rate law, at least what those symbols mean? Okay, well, like I said before, any of these integrated rate laws have an infinite number of points. X, Y
Are the
points.
integrated rate laws only used for reactants, or can they be used for both reactants and products?
The integrated rate laws are derived from the rate law, and the rate law only has terms involving the reactant concentrations.
Okay, thank you.
Yep. Okay, so now having said that, if I know the rate of consumption of a reactant, I can use that other equation that we looked at early on in this chapter that relates the rates of consumption of any of the reactants to the rate of production of any of the products, as well as the overall rate equation. But to answer your question, no, the integrated rate laws just are functions in terms of concentrations of reactants. All right, thanks for asking.
Okay,
Any other questions? Okay, good. All right, thanks. Now, these integrated rate laws, as we had mentioned before, they're an infinite point function. In other words, you give me a time, I'll tell you what the concentration is at that point in time. Now, there's a particular point in time that's kind of special for any reaction. And that particular point in time, that XY point, is called the half-life. Okay. Now, the half-life is defined as the time that it takes to cut the initial concentration, that initial concentration, which is a zero, to cut that in half? How much time does it take to cut that initial concentration in half? Now remember, all these integrated rate laws are infinite point functions. In other words, they relate X and Y, or in other words, they relate T and concentration. Okay, because that's what we're plotting. If you look at each one of these, there's a concentration term on the left and a time term on the right of the equal sign. So that's your X and Y. Now, I want to find the time T 1/2. It's called T 1/2 because it's the half-life. And that's when T 1/2, when the concentration at that time, T 1/2, equals 1/2 of the initial concentration. So that's that one point that I'm looking for. The T 1/2 is when the concentration at some time T equals half of the initial. All right. So all we need to do is take these integrated rate laws and plug that point into the integrated rate law, and then solve for T 1/2. And each time you do that, you get a different equation for the half-life. And we can take a look at one of these right now, and I will in a second. But I just wanted to look at, each one of these half-life equations. So T 1/2 equals that, T 1/2 equals that, and so forth, for the different integrated rate laws. So the amount of time that it takes to cut the initial concentration in half for a zeroth order reaction is dependent on the rate constant. It's inversely dependent on the rate constant here, here, and here. Furthermore, notice that the half-life is directly proportional to the initial concentration for a zeroth order reaction, is independent of the initial concentration for a first order. In other words, it doesn't matter what you start with as far as initial concentration, it always takes the same amount of time to cut that initial concentration in half, independent of the amount you started with. Whereas for second order, it's inversely proportional. That T 1/2 is inversely proportional to the concentration, which is opposite of the zeroth order. So what zeroth order is telling you is the more that you start with, the longer it's going to take to cut it in half. Whereas for second order, the more you start with, the smaller amount of time it's going to take to cut it in half. So that's kind of interesting. And for first order, it doesn't matter what you start with. And this is going to become important when we look at carbon dating, for example, and nuclear chemistry at the end of the course, where we find that all nuclear processes are first order and they're independent of initial concentrations, and the half-life is only related to K, the rate constant, which is related to the type of nucleotide that's disintegrating. And that makes it a very powerful method for dating objects. All right. Any questions on that?
So for the first order, the more you start with, the longer it's going to take. And for the so for the 0th order, the more you start with, the longer it's going to take. And for the 2nd order, the shorter it's going to take, right?
Correct.
Really?
Yeah, isn't that kind of weird, huh? But that's what the equations say. Now, where did those equations come from? I want to show you that real quick and show you what I mean. I mean, I told you, but it's still. Now, somebody out there, pick which one we should look at to derive that half order equation. Should we do the 0th, the 1st, or the 2nd order integrated rate law? What do you think?
Let's start with the 0th.
Okay, so the 0th integrated rate law looks like this. Oh, sorry, that's not 0 there. That's T. All right, now I want to find out, this is an infinite point function. So I want to find out what the equation looks like for T1/2, the half-life.
You're not showing your screen right now. It's just a video of your feeling.
Oh, I see the screen. Yes,
I can see it too.
I see it.
sometimes Zoom will pin the wrong window, so you might have to look at all the participants and manually select the screen.
Oh boy, how do I do that?
Oh no, that's not on your end. It's on the end of the student.
Oh, thank God.
Oh, I got it. I figured it out. Thank you. You're a hero.
Hey, I'm glad that we all figured it out. Thanks, guys. Yeah, because I wouldn't be able to do it. All right. Okay, good. We're set. Any other questions before we get going? All right, so we have that integrated rate law for 0th order, and that's an infinite point function. And I want to find how that function collapses for T1/2 when the concentration of A at T1/2 equals half of the initial concentration. So all I need to do is make that substitution, or make those substitutions. I'll substitute that in here, and I'll substitute this guy over here and see what happens. Now, that infinite point function reduces to 1 point, the half-life point. So here I go, A0/2 equals minus KT 1/2 plus A0. Now, I'm going to solve for, use my algebra and solve for T1/2. And now I should get that equation on the previous slide. So this is 1 point here, 1 point. It's T1/2 comma A initial over 2. That's the point that we're looking for. So I'll subtract an A0 from both sides. So I have a half of A0 on that side. So over here, I'm going to get minus a half of A0 equals minus KT 1/2. So T1/2 equals concentration of A0 over 2K. And that's it. That's where that half-life equation comes from. And you can see back here that it corresponds to the one in the table. Now you can do the same thing for each one of these. Does anybody want to see another one?
Do you mind going back to that screen again, please?
Oh, sorry. Sure.
Thank you.
No problem. How
Can
about
we do
say
the
what?
first order? Can we
Yeah,
do the first order one?
Yeah, absolutely. Let's do the first order one. So let me get another slide. So the first order integrated rate law looks like this: ln concentration of A okay. So again, I'm going to make that substitution for the half-life. So this is an infinite point function. And now I want to do at t1/2. I have ln concentration of A0 over 2 equals minus k t1/2 plus ln concentration initial. Now, I can take that equation and solve for t1/2 by subtracting the initial concentration from both sides, and then using a law of logs that says ln x minus ln y equals ln x over y. Now you can look that up or memorize it or whatever. You can put in values for x and y on the left and put in those same values on the right and make sure that that equation works, that you get the same answer or whatever. But anyway, when I subtract this, it goes to the numerator, or sorry, the denominator. So I get ln A0 over 2 divided by A0. So these cancel. And I can solve for t1/2, which equals minus the negative sign. And ln of 0.5 is that 0.693 value. So again, t1/2 equals ln of 1/2 divided by a minus k. And oops, not the negative, sorry. ln 1/2 is this value right here. And so again, we see the half-life equation for first order reaction is independent of the initial concentration, just like we saw in our table here. And so I'll leave you guys to check out that second order integrated rate law and how you can derive the half-life equation, but they come right out of the equation, just like we did for those two examples. Any questions on that?
I think so.
All right, awesome. Okay, so some of you guys who had calculus might be interested in how that integration process works. But anyway, real quickly, what happens to do this for those guys who have calculus is that you make a new equation that relates, say, the integrated rate law for first order. That's when there's a 1 there, to the way that the rate changes in terms of the change in concentration of a reactant with time, deltas. And so then once I make this equation like I have over here, I equate these two. I can group like terms. So I would bring the delta concentration. I would group that with concentration. So I have to bring that over to this side, and I have to bring the time over to this side. So the equation looks something like this. Okay. And so I have all the concentration terms on the right, all the time terms on the left. And then I could integrate this through time and concentration space. So this would be from some initial time to some final time, some initial concentration to some final concentration. And from integration, we know that this term gives us a log function. So the log function is evaluated from some final minus initial. Whoops. And this just gives us time minus some final time minus some initial time. So this is just t final minus t initial. And the initial time, oh yeah, and there's a minus k out here too. This initial time is often taken as 0, or when you start the clock in lab. You start your stopwatch, you mix the chemicals together and the reaction starts. That's at time 0. So this becomes a KT. And we just bring this negative sign over to the other side of the equation, and that's where this comes from. And this is all by itself over here. So anyway, that's something you don't have to know, because this is a non-calculus based course, but I thought I would just give you that little extra info because these equations seem to appear out of nowhere. But actually it's from calculus, and it allows us to take equations that, like the rate law, that relate the rate of a reaction to the concentration, and make a new equation that now relates the concentration and how that changes in time. Okay, so here we have some experimental data on concentration over here, and how it decreases in time for some reactant. And this also shows how the half-life is constant, independent of that concentration. So it always takes the same amount of time. That's this to this chunk of time is the same as the next half-life, this chunk to this chunk. So this is the same as this one. All right, now this is just concentration over here versus time. If I wanted to see this as a linear function, then the integrated rate law says I can't plot just concentration versus time. I should be plotting the log of concentration versus time, because that's what the integrated rate law says that it should be if I want a linear function. In other words, a y equals mx plus b type of function. So this is the y, mx plus b. And once I convert that data from concentration to the log.
It says pressure of that. Is that just the same as concentration in this case?
Yes.
Okay.
Yeah, so we're using that pressure to relate to concentration. And you know how that works, right? Say it's a gas, and you have PV equals nRT. Concentration is moles per liter, right? So I can divide both sides by V, and these V's cancel out, and then I can divide both sides by RT. So I would get N over V equals R over RT over P. But this is just concentration, moles per liter or molarity. So if I have pressure, right, at some constant temperature, then essentially I have concentration. So this is just another way to say concentration for a gas. Thanks for asking, though. Does that make it any clearer?
Yeah, yeah.
Okay, cool.
I'm sorry, Professor. Isn't it, I might be totally wrong with this, isn't it V over N? So I'm looking at the original equation, PV is nRT, and it looks like it should be V over N. Sorry, I might be wrong about that.
Yeah, the reason why you're wrong is because I moved the V over here on this side, and then I moved that whole side over here. And I brought that
I
V
see.
over there. Yeah, you see, sorry about that. I skipped a lot of
Thanks, yeah.
steps.
So
Gotcha.
wouldn't it be N over V equals P over RT then?
Well,
No,
yeah.
you're gonna divide P on both sides to cancel out. So I divide a P here, they cancel, and the P goes.
Oh yeah,
in
but to
the
cancel
bottom.
the N, you have to, but to cancel the N on the RT side, you have to divide by N, don't you?
All right, I better do this for you guys.
Yeah.
Yeah, sorry about that. Sometimes I skip. Hey, if you don't say anything, I'm gonna keep on going. So it's a good thing that you said something. All right, so I got PV equals nRT. Now I'm gonna divide both sides by V. Okay, so the V cancels here and here. And then I'm gonna divide both sides by RT. Okay, so the cancels here and here. So what I did was I took this and I brought it on that side of the equation. So N over V equals P over RT. Or this is just concentration. Molarity equals P over RT. But either way, pressure, which is what we plotted, is directly related to concentration. And as long as you keep temperature a constant. Okay, so that's it. It's P over RT equals M. Okay. Any questions on that?
So Professor, so these like derivations and what you're doing now, this is not something that we would have to do on an exam, let's say. We just have to know what the final equation is and how to solve for those numbers.
Yeah, most likely, but you should know how to do algebra. And that's all this is.
Okay, got it, thanks.
Yeah, so I just move some stuff around. The point is for our discussion is that concentration is related to pressure. So you tell me what the pressure is and I can tell you what the concentration is. But you have to keep the temperature, and of course the ideal gas law constant is constant. Okay, so changes in pressure is going to give me changes in concentration. All right, good. Any other questions? Okay, so when I take that data, much like you did with your electronic spreadsheet and computer graphing lab report, or that you're doing right now, you took that concentration data and you generated a column of the log of the concentration and another column of 1 over concentration, right? So you take that. Now, if you convert that concentration data to the log of concentration and you get a linear function, that's an indication that you're dealing with a first order reaction process, right? Because now this is behaving like the integrated rate law for first order predicted that it would, where this is y, the log of the concentration, versus time, x. Now, if this was not first order, if it was another order, then this would not come out as a line, this log of the concentration versus time. If it was second order, what would I have to plot here for a line?
One over the concentration.
Yeah, so for second order, to get a straight line, it would be 1 over the concentration, because that's what the integrated rate law for second order says should the relationship should be, right? This guy down here. I have to plot 1 over the concentration versus time, and then this is my y, and this is my x. Okay. All righty. Now, I think having said that, you probably can guess, why you're doing this lab, and specifically part 8 of your report from the lab manual wants you to make this connection between that data that they're giving you in the electronic spreadsheet and computer graphing lab, and they're asking you to tell from that data what the power dependence or what order the rate law is. And so you can do that. Okay. Anyway, this is just an example of some data. And once you get that data, you guys now can use the graphical method for determining the power dependency for the rate order. In other words, by associating with the integrated rate laws, you could tell that a reaction is 0th, first, or second order by the way the concentration changes in time. And so this is another method for finding that order. Remember, we looked at the method of initial rates, where you looked at initial concentrations and initial rates in a series of experiments. And you use that to deduce that power dependency. Well, now you know another way to deduce that power dependency. And that's brought out in the first lab that the online lab, the electronic spreadsheet and computer graphing. Because in that online lab, here, let me just take a few minutes to show you what's going on with that. So the electronic spreadsheet and computer graphing file gives you a bunch of data of time and concentration. So, you have all these points here and so forth, right? And from that, you were supposed to generate the log of the concentration and 1 over concentration. And now you know why. Because if that reaction, if this is reactant A goes to B, if the rate law is rate equals K times the concentration of A squared. In other words, it's second order. Then when you plot 1 over the concentration versus time, what kind of line should you get?
Straight one or?
One here.
Yep. Okay. Now, if you plot 1 over the concentration versus time, and you get something like that, then therefore rate law is not second order. So what the lab has you do is it has you make up these plots of concentration versus time, the log of the concentration versus time, and 1 over the concentration versus time. And so you do that in the electronic spreadsheet and computer graphing, and you get something like this, like that, and then something like this. And so you see right away that, well, geez, the concentration versus time is not linear, so it's not 0th order. The 1 over concentration versus time is again not linear, so it's not second order, but the log of the concentration versus time does give you a linear function. So therefore, you conclude that the rate law is first order in A. Or in other words, it looks like rate equals K times A to the first power. Any questions on that?
If it's 0th power, is that just the concentration versus time? Is that what's linear?
Yes. So if it was 0th power, then the rate law, like you said, equals K. And this plot would look like this. And these plots would be curvature or have some curve in it. Now, what if you plotted all three and none of them came out linear?
And it's on either 0th, first, or second.
Bingo, we have a winner. Yepper. So that's the way you do it. I hope you guys have a little better understanding of what's going on with that lab right now. Okay. All right. This plate here talks about how the integrated rate law for second order was derived, but I'm not going to talk too much about it. Again, you're just going to group like terms, concentrations over here, time on this side. You're going to integrate through time space, and you're going to integrate through concentration space, and that's what pops out according to calculus. We get that relationship. Now, each time, you know, whenever you do a plot in science and you can get a linear function, then you can attribute some of the values from that linear plot to sometimes physical things, meaningful things. For example, if it was a second order type of a relationship, like you have in this case, then the integrated rate law can be compared to the equation of a line because it's linear, y equals mx plus b. And so if you have Excel do the plot for you, then Excel is going to give you some sort of an equation like y equals minus 0.073 time, or x, sorry, that's going to give you x plus, I don't know, 3.56. And so this slope and this intercept that Excel gives you when you make a plot and fit it to a line can have meaning. For example, I see if it's second order and this y was 1 over the concentration that I plotted versus time here, then I see that the slope is related to K. And the intercept is related to the initial concentration. So that value should equal 1 over the initial concentration. So I can solve for the initial concentration if I want. And I could find the rate constant. So you can use the integrated rate law along with this graphical method if you have data to calculate the rate constant K. And so they ask you to do that as well. Now remember, what we did before was we used the method of initial rates and a series of experiments where we changed the initial concentration, and that had some effect on the rate of the reaction. We, from that, deduced or can deduce the power dependency. And furthermore, we can take from any one of those experiments that data and mathematically calculate for K, the rate constant, just like we did, you know, in our previous discussions. But say we don't have a whole series of experiments, we just have one where the concentration changes in time. If we only have one experiment and we have that data, then we can use that data coupled with the concepts of the integrated rate law to calculate the rate law and K. Any questions on that? All righty. Then that's what you're going to be trying, that's what you're going to do for that lab using the integrated rate laws. And again, here we have an example for second order. Here's some experimental data. You see, if I plot log of the concentration versus time, it's curvature. But when I do 1 over concentration versus time, I get a line. Then that tells me that the rate law must be second order. And it also tells me that K equals what?
The slope.
Yeah. Why? Because that's what the integrated rate law says. Here, for second order, remember? That's the integrated rate law for second order. So you see that if I make the analogy for this line, then Excel's going to say y equals mx plus b, and m is going to equal k. And the slope is related to 1 over the concentration. Now note, this is different from when you plot, say, the concentration versus time or the log of the concentration versus time, and you get a linear function. like we did over here. This was the log of the concentration versus time. I got a line. So this time, with my analogy, y equals mx plus b, the slope doesn't equal k. It equals minus k. So for first order and for 0th order, the slope of the line is going to be related to negative k. And that makes sense because look, k's are always positive, and this has got a negative slope. So for that number to be, for k to be positive, it has to equal minus the slope, which is negative. So it's like this equals minus a negative 0.07, whatever. So k equals 0.07 positive. Okay, any questions on that? Okay, now we're going to move on to something a little bit different. Now that we have that integrated rate law down, we know that integrated rate laws associate how the concentration changes in time, whereas just a regular old rate law talks about how the rate is dependent on initial concentrations. So now we're going to move to the rate constant itself, K, and dig in a little deeper into what affects the rates of chemical reactions. Remember, we listed a bunch of things, concentration, surface area, temperature, catalyst, and so forth. And we said, as long as we keep everything the same and only vary concentration, then that's going to give us information on the rate law. Because the rate of a reaction can be found dependent on concentration. As long as you keep everything else fixed and only consider changes in concentration of the reactants. But what's in that rate constant? Well, that's a proportionality constant. As long as you keep everything else constant, it's a constant. But check it out. What if I don't keep everything else? For example, what if I change the temperature? What happens to that rate constant? It's not constant anymore, is it? In fact, it blows up with temperature. So the question is, can we consider what factors affects the rate constant K? And can we do some mathematical magic on it and fit it to some formula that will help us understand what goes into making K and also be able to predict any changes in those factors and how that will affect K and therefore affect the rate of a chemical reaction. And so that's what we're going to get into now. Any questions before we get going? Awesome. We got 20 minutes left before we're going to break for today. So we can get pretty deep into this, I think. Okay, so we know that there's some sort of a relationship between this K, the rate constant, and some other factors like temperature, effect of a catalyst, and so forth. In fact, all the other things that we kept fixed go into K, and thus far have only been looking at changes in temperature, changes in concentration and its effect on the rate. Well, to understand this a little better and to give us a little picture in our mind, we do what most scientists do, and that is they try to think of simple models that will help them understand things that take place on the molecular level. So a lot of scientists were doing this back at the turn of the century. Arrhenius was one of these guys. And he found that by considering just a simple model, the collision model, for how things react, we can get a picture and a better understanding of what goes into changing K, the rate constant. All right, so what is this collision model? It's very simple. It says that for reactants to react, they have to collide. They have to come in contact. So if I have some reaction of A plus B, they're both look like homonuclear diatomic molecules in this picture, and they collide, will they react? You know, what are the factors that determine whether reactions react or not? Well, not always. They could collide and just bounce off of each other and go their merry ways, or they could collide and make products. These products are AB. Okay. Now, this simple collision model will tell you why at higher concentrations, the rate would be higher. Why? Because you have more collisions. If you have more collisions, then hey, it makes sense that statistically, more molecules are going to be successful at reacting. Also, it kind of gets at why higher temperatures tend to increase the rate of reaction. Why? Because if you have higher temperatures, those molecules are moving around more quickly or with a higher kinetic energy. So when they collide, they're going to collide with more energy, and that's going to lead to higher rates of reaction. So you see right off the bat that collision theory at the most basic level helps us visualize and understand why reaction rates would increase when you increase the concentration or when you increase the temperature. Any questions on that? All right, so what else can we understand from this very visual and relatively simple theory or model of collisions? Okay, again, we go back. They collide. Do they react? Maybe, maybe not. Well, geez, what does that depend on? So Arrhenius was thinking about this, and he goes, well, maybe when they collide and they don't react, they just don't have enough energy. So the question is, well, geez, why do they need energy to react? Where's that energy going? Does anybody have an idea of why atoms need energy or molecules need energy to react?
We need energy to
Break the
break and
bonds.
reform bonds.
Yes, bingo. You need the energy to go into breaking those bonds in the reactants. Now, this also implies that when new bonds are formed in the products.
So does that mean activation energy is synonymous with the energy needed to break bonds?
It is related to the energy needed to break bonds. Yeah. Okay, so Arrhenius coins this phrase, the activation energy. And he says this is the minimum energy needed to break the bonds during a reaction. And so he, after realizing this, he wants to get a picture of how this would look for a reaction. So he proposes this potential energy curve that looks like this, where On the y-axis, we have energy plotted. And on the x-axis, we have what's called the reaction coordinate, or sometimes the reaction pathway. You can think about it as time goes on during a reaction. So here we start with some reactant, and over here we finish with some product. Now this is a simple reaction. It's just a rearrangement reaction. Notice that in the reactant, we have a carbon-nitrogen bond here, and in the product, that switches to a carbon-carbon bond. So this part here rearranges and bonds to this carbon over here. Okay. And this potential energy surface, they call it, this is a two-dimensional potential energy surface. So the two dimensions are energy and this reaction coordinate as the reaction proceeds from reactants to products. So that's the reaction coordinate. In reality, this is a multi-dimensional hypersurface.
Wait, what are the two coordinates? Potential energy and what?
As the reaction proceeds.
No, well, what are the two coordinates?
That's the two coordinates. One is energy. The other coordinate is as the reaction proceeds. or
Okay.
reaction pathway. Yeah. And so this coordinate here kind of involves a whole bunch of things. If you want to break it down, but in general, since we can only visualize in 3 dimensions and in a flat surface only 2, it's advantageous to just look at these 2 dimensions, the energy versus as the reaction proceeds from reactants to products. Okay. So we start off with some energy with the product, with the reactant. And this energy can be calculated in many ways. One way is to take that reactant and just blow it apart and see how much energy is released from the combustion. Another way to get at this initial energy is to use quantum mechanics and first principles to calculate all the interactions involved in that molecule and so forth. So there's different ways to calculate these energies. Now, as we go from the reactant to the product, what Arrhenius envisioned is there had to be some sort of a collision. This reactant collided possibly with the walls of the container, or maybe another reactant. And so during that collision, the kinetic energy, it was traveling in that sample, the kinetic energy is converted to potential energy. So energy gets concentrated in the bonds. And bonds need to be broken, like this one here. And bonds are going to be formed in the product, like that one. Now, the best guess to the transition state structure, or what's also known as the activated complex, that's the geometry right here at the tippy top point. That transition state geometry is most likely, and you can get your best guess at what it looks like, as an average between the reactants and the products when there is a simultaneous breaking of the reactant bond along with the simultaneous formation of a product bond. So you'll often see activated complexes with a ... kind of a form showing that bonds are being broken. In this case, the carbon-nitrogen. At the same time, a carbon-carbon bond is being formed. Usually you won't see these dots here in the middle. So this is the best guess to the transition state geometry, which corresponds to the tippy top point of the minimum energy path. So what the hell does that mean? Okay. Imagine that you're in the Grand Canyon and the Colorado River, and you're lucky enough to be there. I've never been there, maybe someday after I retire though. And you're flowing down that river and there's a high point, but it's way down in the valley. So all other directions, there's sheer straight upward walls. And so that river is following the minimum energy path. And you can imagine that the river goes and it hits some high point and the water's going to fill up, right? It's going to fill up until it gets over that high point. And then once it's over the high point, boom, it goes down and goes on its merry way. That's what this minimum energy path is. All other paths from reactants to products are higher in energy. This is the minimum of all of the possible paths, which is why it's referred to as the minimum energy path. Are there any questions on all of this stuff?
I think I'm good.
Okay, cool. All right, now, this minimum energy path requires the activation energy, and that can be calculated, as you can see from this diagram. All I would need to do is take a ruler, come over here, find out this energy. That's going to be the energy that refers to the activated complex geometry. And I would just subtract from that energy the energy of the reactant, and I would get the amount of energy required to get over that hump. That's the minimum energy or the activation energy. Now notice that that energy calculation is different from an energy that you probably have seen before in Chem 200, and that is the change in energy, or sometimes this is related to delta H when the energy that's given off is heat, or when heat is absorbed. I can see this is an exothermic reaction because the energy of the product here, which I would find by bringing a line over here, this would be the energy of the product versus the energy up here of the reactant. I could see that it goes down. So final minus initial, this is going to be negative. And that makes sense because it's exothermic. If it went through an activation barrier and the product energy ended up somewhere up here, then it would be endothermic. And final minus initial would give me a positive number, and delta H would be positive.
Would the activation energy also be released as kinetic energy?
The activation energy is absorbed by the molecule. Okay, this is the minimum energy needed to break the reactant bonds while at the same time forming the product bonds. That's the minimum energy. So that's absorbed. All right, any other questions? Okay, so this is a picture of how Arrhenius is understanding the energy effects as a reaction goes from reactants to products, or at least the energy requirements. Okay. So we've talked about all of this stuff already. Go through that. And we talked about how to calculate the change in the reaction, which is sometimes referred to as delta H, and how that's different from the activation energy, which is that transition state energy minus the initial. All right, so this collision theory and these models indicate how the rate K, the rate constant K, can be dependent on temperature, also can be dependent on the activation barrier. And we took a look at how orientation a little bit would be important, and also the collision frequency, how many times those molecules collide upon reacting or before they react. Okay. All right, now, Arrhenius gets together with a math friend of his, Boltzmann, and tells him about his thoughts. And Boltzmann says, well, geez, I know a way how you can model mathematically that fraction of molecules that have that very important energy, the activation barrier. Just look at statistics, Boltzmann says. And he shows that I can model a collection of molecules or particles, whatever you want to call them, and their energy distribution within that collection. Boltzmann says here, look, at a lower temperature, I have a Boltzmann's plot that represents that collection of molecules, for example, or particles, whatever you want to call them. And if I increase the temperature, so this first plot is for the low temperature, if I increase the temperature, then my mathematical formula will model the energy within that collection of atoms or molecules. And it shows that the distribution of energy, we call kinetic energy, spreads out to higher energies at higher temperatures. So I have here the fraction of molecules versus the energy. Here is the mathematical formula that Boltzmann has shown to Arrhenius, and how that mathematical function uses the activation energy, that important energy for the collection of molecules, as well as the temperature at which that collection of molecules exists. And the number of molecules is associated with the area under each curve. So as you increase the temperature and the curve hunkers down and shifts to the right, then you see that on average, for example, since these are both right-leaning curves, the average energy in this first collection is right around here. But if I increase the temperature, then the average energy increases, as it should, right? But the important energy in this collection is neither one of those, not the average. It's EA. This is the important energy. But since this models collections, energy of collections of molecules, we can see that when you increase the temperature, the fraction of molecules with a certain energy, namely the activation energy, increases. And it shows by how much. See the red right here? That's on top of what the blue was for the colder temperature. So the area under the curve is now greater for this point onward at higher temperatures. And so Boltzmann can mathematically model what the temperature effect is on the fraction of molecules that have that energy. And the energy that's important is the minimum energy, or EA. So Arrhenius says, oh man, that's exactly what I need. That's what I'm going to use to model my collection of molecules. And I'm going to model the rate constant K in terms of this mathematical function. The other things that are important are the orientation factor and the collision frequency, which all go into A, this pre-exponential part. And then we have these other parts that Boltzmann helped Arrhenius, along with collision theory, understand their effect on K. So now K, the rate constant, is not constant with temperature. You put in a different temperature, I get a different rate constant. And the rate also changes if the activation barrier changes. So let's stop there. We'll come back, recap the results of the Arrhenius equation at our next meeting. And I'll just open it up for questions now. You guys have any questions?
Not yet.
Not yet. So, all right. So thanks for your attention. See if you can understand that. We'll meet on Wednesday, go over any questions that you have, and continue from there.
Thank you.
Thank you, guys.
Thank you.
All right, take care.
No question, Professor, but I want to say I was in the Grand Canyon the other year for 30 days. I whitewater rafted down the Colorado River.
You're so lucky.
I am. It was amazing. I made friends with a group of river guides when I was in Oregon one year, and they just went on to the river yesterday. So they do like an annual trip.
Wow. I want to do that, man.
Yeah, so
For a whole month?
yeah, it was great. It was me and 5 other people. And we only saw like 2 other groups, and they were kayakers.
So did you camp down there too?
Yeah, we camped down there the whole time. Everything we brought down, we had to bring back up. And but yeah, it was amazing.
Oh, what a blast.
Yeah, so I definitely recommend it if you ever get a chance.
Oh, I will.
Yeah. All right. Thank you, Professor.
Thanks for the info.
Bye.
Bye.